Okay, we did. So we'll finish up that example that we wrote down last time, where we had a cylinder with radius equals 20, h equals 10, possible error in each was 0.01. So these aren't measured as accurately as possible. That's the possible error in each measurement. And we want to know what is the error in finding volume and relative error in finding volume. And here we're going to apply differentials, so I want you to see an example of how you would apply that. If you're asked to like approximate some number like the cube root of something weird, I'd probably use the linear approximation way of doing it, but it's very customary to, in word problems like this one, to use the differentials way of looking at it. But as I said, they're both kind of the same thing. But anyway, let's get into this. So we have a cylinder here, and we want to measure its volume, and we have possible errors here. So note, we can think of the error as it's the difference in volume between what this would be with the actual measurements and what it would be with these increased measurements. And so we can think of the error as really just a change in volume given some changes in the radius and height. Okay? So someone manipulates the radius and height, and we want to know how does the volume change in reaction to that manipulation. And so here we can have an equation. The volume, well, it's a circular cylinder, so it'll be pi r squared h. And similarly, we can find the differentials by taking derivatives. With respect to each of these variables, we get dv equal to 2 pi r h dr plus pi r squared dh. This is kind of a multivariable way of doing things. One way you can reconcile this with what we've been doing in Calc 1 is to, you can imagine that we're taking the derivative with respect to time everywhere, so there's a dt under all of these, and then we multiply it through by dt to kill all the dt's, because we don't care about time. And the Leibniz notation is convenient like that. There are theories about why you could do this directly and just look at the differentials without worrying about with respect to what. But that's more like multivariable calc where you'll talk about something like that. But ultimately we can do something like this, a very familiar maneuver hopefully. And basically the change in R is going to be the possible error in R. And the change in H is the possible error in H, which we're given as these numbers. And so we can actually find the change in volume directly by actually just plugging in the values. So when dr is 0.01, dh is 0.01, our dv is going to be 2 pi r, 20, h is 10, dr is 0.01, plus pi r is 20, dh is 0.01. and then we simply compute. So this is going to be 200 divided by 100, so that's just 2. And so we have 4 pi here. And this is going to be 400 divided by 100, so that's just 4 pi here. So you get 8 pi, and it's a volume, so this would be in cubic centimeters. Right? That's how much will be off from the actual volume. The maximum amount we can be off is by 8 pi units. Which means whenever someone actually tells you, oh, we think the volume of the cylinder is this, well, it means, well, they could be wrong, give or take 8 pi units. And now if you want the relative error, this is kind of like a percentage error. That's going to be the change in volume over what the actual volume is. So you're looking at the change as a measure of the total. And so here, you can have this is 8 pi divided by the actual volume is going to be pi with the actual calculated numbers plugged in here. And that's going to be 400 times 10, that's 4,000. Pi's would cancel. 8 also goes into this, so it's 1 over 500, which is what, 0.002 or something like that? Is that 2 zeros? I can't bother thinking about it. Which you can think of as 0.2%. Which means if you know the errors in each of these dimensions, the error in whatever, in calculating the volume using these dimensions, you'll be off by 0.2%. And of course, the application to this would be sometimes in certain situations, there will be a maximum tolerable error, right? So you'll have guidelines as to say, okay, we'll allow an error of this much but no more. And if 0.2 happens to be too big, we have to do something, right? And if it's okay, then you kind of just leave it. And leave it up. A lot of engineering is kind of like that, actually. So when they're building a bridge, they know that they're never going to be accurate. So they kind of set up some tolerances, and they kind of over-engineer things. So they're like, what's the worst possible scenario? Okay, make our error larger than that. And so they can actually design things safely. But some of these calculations will go into the background. You can actually use calculus to talk about if you have errors in all these pieces and you're using all these pieces to do something else, how do you find the error in that new thing? And differentials is a way you can actually do that. So that's just to use the last example. And again, we call these guys the d of a variable differential of the variable. So this is the differential of the differential of r, the differential of h. Okay, so that's why this is called differentials. So that's just finishing up last time. We're actually going to move on to something different. Unless there are any questions? Any more questions about this? So we're going to talk about some very important topics. Maximum and minimum values. The different kinds there are. We're also going to get some nice theorems out of here. Some of these theorems that we'll talk about here will be used to prove other theorems that will be used to prove the fundamental theorem of calculus. So it's actually an important section to know about. That's the new topic. We're going to talk about maximum and minimum values. There are two kinds of maximum and minimum values that I want to kind of talk about. There's the absolute or the global ones, and the local or relative ones. So let's actually talk about that. then we'll talk about how to find them. So, definition. F of x is said I want to define a domain first. Defining what it is to be an absolute maximum or global maximum. It means there is some value of the function that is larger than every other, larger than or equal to, than every other value of the function in this domain. Okay? So there is such a thing as a maximum y value across the entire domain. There is some guy who's bigger than everyone else. Right? If such a guy exists, we call it the absolute maximum. Or global maximum. This is the guy that's bigger than everyone in general on the domain for which the function is defined. Similarly, f has an absolute or global minimum at x equals c if that value is less than or equal to f of x for all x in B. So if you look in general on the entire domain of this function, if you can find some y value that's larger than everyone, we call that the global maximum. If you can find a y value that's smaller than everyone, you call that the global minimum. So another definition. And I'll illustrate what these guys look like. And this one is kind of going to be a little fuzzy because we're going to use kind of limiting language here. But f is said, and again, we're assuming our function is defined in D, to have a local or relative maximum at x equals c if f of c is greater than or equal to f of x for all x near c. Okay. So there's such a thing as talking about a local maximum or minimum, or a relative maximum or minimum. Similarly, we can define the relative min. But this one, the distinction between this and the last one, which I'll draw some pictures to illustrate, is that this one is very local. You're talking about only points that are near this as you kind of zoom into that point. Whereas the absolute, it's like you look at the entire thing and pick out the biggest, baddest guy out of everybody. Okay. Similarly, f has a local minimum at x equals c if f of c is smaller than f of x for all Let's look at some illustrations here. Make sure that we understand these definitions. Now I drew several. I might just make up some other ones too. So. Examples A, B, suppose that's the domain. There are many more pictures I could draw, but let's just look at those. And let's just say let's just go through these pictures, identify all these points that I just defined, make sure that we actually understand what these guys are, how to recognize them on a picture. Okay, tell me about the absolute and local maximums and minimums here. Where would you say they exist? Are there any absolute minimums on this picture? Where would they be?
X equals 0.
Huh?
X equals 0.
X equals 0?
Like
You mean
where
over here?
A and B are.
Oh, where the y equals 0?
Yeah.
Like
Y.
the locations of A and B?
Yeah.
Do you think of those as absolute minimums? By the way, they're also local minimums. Although that's kind of implied. If something is an absolute minimum, it will also be a local minimum. Right? If you're the smallest in general, you're definitely the smallest among the people who are close to you. you can look at this guy here, at that peak, and that will be the absolute maximum. Because you'll notice that for the entirety of this graph, that is going to be the highest y value attained. It's also a local maximum. So you pretty much look for the smallest guy out of everybody, that's your absolute minimum. In this function, it is 0. Y equals 0 would be the absolute minimum, and the absolute maximum will be whatever y value is here. That'll be the absolute maximum. Okay? You can talk about this guy here. Again, this here is going to be your absolute minimum, which is also a local minimum. The guy over here is your absolute maximum. It's also a local maximum. This guy over here, again, the lowest y value attained is the local minimum. It is also an absolute minimum. Although the points that I'm identifying as both, you'd probably identify them as the absolute because the absolute already implies local, but it doesn't work the other way around. What is the absolute maximum of this picture here? There is none. There is no absolute maximum here. In fact, there's also no local maximum. Right? Why? There is no largest y value. Anytime someone tells you a y value, eventually this curve surpasses that. No matter what y value you pick, this guy is just going up asymptotic to this line here. There will be no absolute maximum. Right? So these things don't have to exist. Similarly here, this actually has neither. There is no absolute max. There's no absolute min. There's no local max. There's no local min either. This guy has none of these properties. We can look at this one. And you notice that here, this y value is slightly higher than this one. Therefore, this point here is going to be your absolute minimum. Right? It's also a local minimum, but let's just call it an absolute minimum for now. You can talk about this guy here. Well, that is a local maximum. So is this guy. So is this guy. So is this guy. You can talk about local minimums. Those will be guys here, here, here. Is there an absolute maximum? Where would that be?
Not at this point.
Like on the third hump right here. Okay? So this guy I would think of as an absolute maximum. Right? He's the guy that gives the highest y value out of everyone. Now, this kind of shows you the distinction because you have both kinds here. You'll notice that what local really means is if you zoom in and focus on that guy and ignore the rest of the graph, that point is the highest point locally. All other y values near him are smaller than him. Okay? The same thing would happen if you zoom in here, zoom in here, zoom in here. That would be the same thing. The distinction between a guy like this and a guy like that is this guy is the biggest when you look at everything overall. And therefore we call that guy the absolute maximum. He's the global maximum. He's the largest there can possibly be on the entire graph. Okay? But you can have these local bumps or these local valleys where if you zoom in, you can see a lowest point or a highest point. And that's really the distinction. Both of these kinds of points are very important to figure out when they occur, by the way. But I just want you to know the difference between the two. Similarly here, we can think of this as a local minimum. This guy here will be the absolute minimum. He's definitely smaller than everyone. This guy here will be the absolute maximum. You'll have local maximums here and here. You'll have a local minimum here. You'll Also have a local minimum there, but the absolute supersedes the local because absolute implies local. But local, of course, doesn't imply absolute. Okay, so that's kind of the difference. So this is the behavior of the functions that I described a little bit earlier. Oh, they didn't set the clocks. So just want to make sure that we understand, at least as an idea, intuitively what these guys are. Make sure that we understand the definitions. What about this example here? And then we'll start doing some calculations. Okay, let's look at this example. Here's the y-axis. X-axis. What kind of properties does that have? This does. Is there an absolute minimum?
No.
No. There is no y value on the entire domain of the graph. Because you'll notice that here, y values keep getting smaller and smaller and smaller. No matter what y value someone tells you, something will get, there is going to be a y value that's smaller than that guy. What about absolute maximums?
Yeah.
So this has no absolute minimum. It also has no absolute maximum. Now you might start to think that, well, this guy looks like the highest point on the graph. But you should notice that that point is actually not in the graph. So in other words, our y values keep increasing towards that guy, but they never actually make it. So no matter who you say, no matter what y value you say in this function, there is going to be a y value that is larger than it, getting closer and closer to this point, but of course never reaching it. We do have a bunch of locals though. This would be a local max, local max, local min, local min, local min. What about this guy? What do you think that guy is?
Which?
This point right here. Is it a local max or local min or something else? Well, that one is neither, okay? And how you'd recognize that as neither is you look at all x values close. Now, when we talk about x values being close, we mean we open up a very small open interval around that guy. You will notice he has points in that interval that are higher than him, namely on the left side of the graph. He also has points that are lower than him, right? So he can't be the absolute minimum because there are points that are lower, and he can't be a local minimum because the points are lower. He also can't be a local maximum because there are points in a small interval that are higher. So that guy is actually nothing. That's kind of faking out right there. And functions can have all sorts of these behaviors. Now, let's actually talk about let's jump into examples now and then tell you about extreme value. I think we'll jump to the theorems. So, now regarding this discussion of absolute maximums and minimums, there are two important theorems for us. One is a super important theorem. It's called the extreme value theorem. We're not going to prove it. The proof is a bit involved, to say the least, but it's a very important theorem. You can use this to prove theorems that you would need to prove the fundamental theorem of calculus. So that's just one way in which it's an important theorem to know. This extreme value theorem asserts the existence of maximums and minimums. So the theorem says if f of x is continuous, and we know what continuous means on AB, right? So we're saying that there is a function that is continuous on a closed interval, then f of x will attain absolute maximum and an absolute minimum on AB. It's possible that, and in some of my examples you actually see this, possibly at the endpoints. So it's somewhere on the closed interval it will attain this. So as you can see, we did examples that had neither. For example, this one has neither an absolute minimum or an absolute maximum, and that was because this function is just not continuous on the interval that we were considering. There are breaks, there are gaps on the function on this interval. But it turns out, if you know your function is continuous, which now we know how to check that, you are guaranteed to have an absolute maximum and minimum of that function. There's no way you can't, right? It's kind of the mathematical way of saying what goes up must come down. You can't just keep going up forever. If you're a continuous function on some interval, you have to come down at some point and stop somewhere. It's called the extreme value theorem. It is a super important theorem, but we're just going to mention it and run with it. Now, here's something else that's interesting. And then we'll get into some examples after I talk about this one. Now, so let's talk about some function that's defined on some domain, and we know it has a local max at on that domain at some point C. I'm also going to assume that the derivative actually exists, so it's differentiable where we're considering this. Then here's something strange that will happen, or interesting that will happen. ultimately, these points are important. We're going to want to know how to identify them and find them, and these two theorems are going to tell us how to find them. So, suppose it has a local maximum. This means f of c is going to be greater than or equal to f of x for all x near c. Now, since x is near c, we may write x is equal to c plus h, where h is small. So think of your x value as c plus or minus a little bit. That h can be a positive or a negative value. This will, of course, mean that f of c is greater than or equal to f of c plus h. In other words, we would have that our f of c plus h minus our f of c will be less than or equal to 0. Now there are two cases. Depending on whether x is to the left or the right of c, we can say h is greater than 0. That would mean that if I were to divide both sides by h, the inequality sign will remain the same, in the same direction. And so I can take the limit as h approaches 0 of this limit as h approaches 0 of both sides. And you'll notice that that gives you the derivative evaluated at c. And you'll notice that this would mean, of course, that your f prime of c is less than or equal to 0 in this case. Case 2. If your h is less than 0, and so let's say this is 1, then dividing 1 by h gives f of c plus h minus f of c all over h. Divided by a negative number turns the inequality sign around. And so what we can do is, again, we can take the limit as h approaches 0 of this. And of course that implies the derivative is greater than or equal to 0. So now taking these two facts together, we've shown that your derivative can be less than or equal to 0. It can also be greater than or equal to 0. This implies, by the squeeze theorem, your f prime of c must actually be 0. It will have no choice. And that's our first clue of how to actually get to these maximums and minimums. The derivative might have something to do with it. Okay. So, well, this is similar practical is true for local minimums, where f prime exists. right? You'll do the same kind of thing. If it's a local minimum, this guy will just be flipped the other way. Do the same kind of maneuver, you'll find exactly the same thing happens. You'll find that your derivative has to be 0 there. And this proves another very important theorem. Proves what's called Fermat's theorem. Yes, the same guy who came up with Fermat's last theorem, which took like 300 years to prove. Which he claims that he had a proof for, but he never actually wrote it down. Drove a lot of people crazy. For a very, very long time. Until Andrew Wiles, I believe of Oxford University, proved this, mid-90s maybe? But this is a different theorem of Fermat, and it basically says if f has a local max or min at x equals c, and f prime exists, then f prime of c must be 0. That's the statement of the theorem. That is Fermat's theorem. Some vocabulary words I should have probably introduced earlier. Sometimes max or min values are referred to as extreme values. And extrema is a plural. So in other words, if someone asks you to find the extreme values, or find the local extrema, or find the absolute extrema, they're really talking about the maximum and minimum values. It's just another way to do it. So Fermat's theorem basically says that if f has a local extrema, extreme point, and f prime exists, then f prime equals 0. Okay, so that's Fermat's theorem. Now, it's very important for you to note that the converse of this statement is not true. The converse of a mathematical statement is simply the reverse statement. Okay, so knowing that the derivative is 0 does not tell you that f has a local max or min there. And I can give you an example here. Look at f of x equals x cubed. Notice that f prime of x equals 3x squared. F prime of 0 equals 0. But if you know what x cubed looks like, that's not a maximum or a minimum. Right? X cubed looks like that, 0 is there. There are points both lower than it and higher than it. X equals 0 is not a, x equals 0 is not an extreme point. Right? So knowing the derivative is 0 doesn't guarantee you a maximum or minimum, but the other way works. If you know there's a maximum or minimum, you're guaranteed that the derivative is 0. There are, of course, other cases also. What if f prime does not exist? Fermat's theorem talks about the case where f prime does exist. And you can notice that we could have maxes or min here. And we've seen an example here as well, the absolute value function. So notice here we have a local min at x equals 0, but f prime is undefined there. Okay, so now we're starting to get some ideas. The idea is there are two places that we would probably want to look when we're trying to find extreme values. Clearly, where the derivative is 0 might be a candidate, not guaranteed, but it's worth looking there. And clearly, if f prime does not exist, that could also be a situation where you find maximums and minimums. So points where these two things are true are for us going to be very important points to determine. Where is the derivative 0 versus where the derivative does not exist? And because these points are important, we will give them a name, definition. This is what is called points that have either of these properties. We call them critical points. There are two situations that we'll call critical. It's critical that we find these points, and these are called critical points. They're kind of the guys that we're going to check when we're looking for maximums and minimums. So Fermat's theorem indicates that this is an important place to look, but examples like absolute value of x also indicate that these are important places to look. So if you're looking for a maximum or a minimum, you're going to check one of these two spots. You're essentially going to find the derivative, set it equal to 0, or find the derivative, figure out where it's undefined, and those are the points you're going to check if they're maximums or minimums. And that ends today. We're kind of on a cliffhanger, but we'll pick up tomorrow with this idea. I'll see you guys. So, yeah, we have a quiz tomorrow, and it covers up to, I don't remember, I already wrote it. Covers up to what we did up to last week, I think. I don't think I put any of this stuff on there. But in that case, I will see you guys tomorrow morning, bright and early. We'll start to do some examples with things like this.